Hi guys, I'm Monica. Welcome back to my channel Aeroker. So this video, let us start with a theorem which we had left as a surprise in our previous video, and that is nothing but the Kutta-Joukowski theorem. So in order to understand this theorem more clearly, let us have a look at the airfoil. So what we are going to do here is we are going to consider an airfoil section. As you can see here, we are going to consider an airfoil section, and the flow around the airfoil will be our incompressible flow. So around this airfoil, let us consider a curve A. So this curve A is any curve in the flow which is enclosing the airfoil. So if I say that the airfoil is producing lift, then the velocity around this airfoil, it will be such that the line integral of velocity around A will be finite. So if I have to represent this mathematically, when I say the line integral of velocity will be finite, which in turn tells me that my circulation will be finite. So this we get as VDS, which is nothing but, so circulation can be written as gamma is equal to line integral A VDS. At the end of our previous video, we had seen a formula for lift per unit span, or the expression for lift per unit span, which is given by rho infinity V infinity gamma. So this was our lift per unit span, and as I had told you that this indicates a theorem. So this expression is given by the theorem which is known as the Kutta-Joukowski theorem. Let us say this is our equation 1. So if we look at the equation, what does this theorem state? It states that lift per unit span on a two-dimensional body is directly proportional to circulation around the body. So previously we had considered lifting flow over a cylinder by superimposing a uniform flow, doublet flow and a vortex flow. Also we had considered other elementary flows such as irrotational, which is irrotational at all points except for the vortex, which has finite vorticity at the origin. So therefore, when I say lifting flow over a cylinder is irrotational at every point except the origin, because it was superimposed using a vortex. Now, if we take circulation around any curve that is not enclosing the origin, any random curve I'm taking and it is not enclosing the origin. So if I use the equation, this which we had derived previously, so if we refer to this equation and we are choosing a curve, now in case if we choose a curve that is enclosing the origin, then this will have an infinite value, and in case the term in the brackets, that is curl of V, has an infinite value, circulation has a finite value which is equal to the strength of the vortex. The same thing applies to the airfoil as well. If the curve is enclosing the origin, then circulation will have a finite value. Now, the flow that is outside the airfoil is irrotational, and the circulation around any closed curve which is not enclosing a airfoil or any origin, then the circulation will be 0. Let us have a detailed look at it. So, for example, here is the airfoil, and we have an enclosed curve around this airfoil over here, and the flow beyond this we consider as the flow outside the airfoil. So outside the airfoil, as I said, the flow outside the airfoil is irrotational. So let us consider this curve B over here, which is an enclosed curve. Okay. So when I say that this enclosed curve, as you can see, it is not enclosed within any origin, or you don't have any airfoil inside it. So I can write integral of B, BDS is equal to 0. In case this curve is enclosing the airfoil, As we said in the equation, the circulation will have a finite value. So therefore, by looking at these statements, what we can say that in the Kutta-Joukowski theorem, the value of circulation must be evaluated around the closed curve that encloses any body. If it is enclosing any body, then only you're going to get the finite value for circulation. Now, we saw about this Kutta-Joukowski theorem. We got the equation for lift per unit span. What is the purpose of all this? Like, why are we studying all this? So, the purpose is to use this approach using the definition of circulation in order to obtain lift is the motive of this theorem. But this circulation theory of lift, it is an alternative way of thinking about the generation lift over an aerodynamic body. But the true physical sources, if we consider in case of an aerodynamic body which generate lift, the true sources are pressure and shear stress distributions that are being exerted on the surface of the body. So this Kutta-Joukowski theorem, it is an alternative way of expressing the consequences of surface pressure distribution. By looking at this theorem, if you're going to make a statement like the lift is caused by circulation or the lift is generated because of circulation, it is not actually proper that you can use this statement. Rather, the reason why we see lift in an airfoil is that the net imbalance of surface pressure distribution and circulation. So these are the two reasons. You cannot just mention circulation. So how do we relate this? If you see our equation 1, so this equation 1 is giving the relation between surface pressure distribution, which is producing lift per unit span, and circulation. Now, if we are considering a compressible flow, as initially we saw over here, we are considering an incompressible flow. If I say that my flow is compressible potential flow, then it is a much easier task to determine circulation around the body rather than calculating the detailed surface pressure distribution, which is known as the circulation theory of lift. So if we consider a two-dimensional body in theoretical analysis, if we are performing any theoretical analysis in order to calculate lift, what is usually done is, in case of two-dimensional bodies and when you have an incompressible inviscid flow, it focuses on calculating the circulation of the body. So once you obtain the circulation, you obtain the lift per unit span using the Kutta-Joukowski theorem. So this was all about Kutta-Joukowski theorem. Thank you for listening. Stay tuned.